think we are all indeed very fortunate to have witnessed this very momentous occasion. And it was really heartwarming to hear our Honorable Prime Minister's address, especially to the youth. I hope the students noticed that he has entrusted so much of he recognizes your talent, and therefore he has entrusted so much of responsibility on all of us in academic institutions and particularly to the students. So with that, I think we will all rise for the Kulgeet. And then we will proceed with the rest of the program.
जयति जय जय जयति जय जय ज्ञान का लोक अनुपम
श्रेष्ठ सुंदर दिव्य दिल्ली विश्वविद्यालय विहंगम
जयति जय जय जयति जय जय ज्ञान का लोक अनुपम सकल वसुधा निज कुटुंब की भावना संस्कृति सनातन आधुनिक शिक्षा पुरातन ज्ञान धाराओं का संगम
देश की स्वाधीनता हित भूमिका शतकोटि वंदन
निष्ठा धृति सत्यम के मंगल दिव्य भावों का समागम
जयति जय जय जयति जय जय ज्ञान का आलोक अनुपम
भव्य महाविद्यालयों के परिसरों से चिर सुशोभित श्रेष्ठ गुरुजन कर रहे नित्य छात्र और छात्राएं दीक्षित
सदचरित्राचार पावन साधना संकल्प संयम
नवल वैश्विक चेतना नव क्रांति संस्कारों का उद्गम जयति जय जय जयति जय जय ज्ञान का लोक अनुपम
श्रेष्ठ सुंदर दिव्य दिल्ली विश्वविद्यालय विहंगम
जयति जय जय जयति जय जय ज्ञान का लोक अनुपम
ज्ञान का आलोक अनुपम
ज्ञान का लोक अनुपम
ज्ञान का आलोक अनुपम
May I now request Dean Colleges Professor Balram Paniji to address the gathering.
Namaskar, good morning to you all the dignitaries, professors, deans, and head of the departments, principals, and my dear colleagues, student friends. Today it is the great opportunity. We have already, we have seen that, there are 3 semiconductor plants have been, that the Selanas has been taken place, and that is to layman, what is the semiconductor and what is the application of the semiconductor? Why it is so important? Semiconductor, it is the only one wherever there is the switch, whenever we switch on and off is required, means their semiconductor is used. And in our country, that is the semiconductor is the only one which one can control and monitor the electricity flow. That electric current, wherever it is flowing, that semiconductor it is controlling and monitoring. That's why it has the importance. And it is used, means almost all the electronic gadgets. So our country is the very vast country, and almost all, means from the rural village level to the urban area, means everybody is used one way or other, means any type of electronic gadgets. So that's why it is very, very important to everybody. So right now, we don't have such type of semiconductors which can help us, which can make us Atmanirbhar, that is the self-sufficient. Means it is the huge amount we are importing. But right now, the manufacturing sector, they have come forward to manufacture the semiconductor chips right now. Means from today onwards, we'll look forward and we'll move in that direction. And definitely it will be a great help to our country to become a self-sufficient and whatever it is saying that in the economy will be the global leader in that field also. And science and technology, means whenever we will talk about the science and technology, science is the probability and technology is the reality. Means whenever the science is saying that okay, this can be possible, and technology will say that okay, right now it is the reality and we are doing so. So science and technology both are going simultaneously, and definitely it will be a great help. And you have invited me, I am thankful to you. And again, I wish you all the best. Thank you.
Right. You know what the market is, the semiconductor market? In valuation, it's almost, or maybe more if I'm right, a $1 trillion market. So it's very important that we join this. Now it's time to hear some developments that are happening, work on in the semiconductor sector that's happening closer home. And for this, we have a very special speaker from Defense Research Development Organization, the DRDO, which all of you have heard of. And we have today with us Professor Raval, who is a very senior scientist in the Solid State Physics Laboratory, which is our neighbor. It is a DRDO lab. And we know DRDO is a part of the Ministry of Defense and devoted to development of advanced semiconductor materials and devices. Dr. Raval, he has got vast research experience of more than 30 years in developing compound semiconductor device technologies for microwave device applications. These semiconductors include gallium arsenide, indium phosphide, gallium nitride in various government projects. Dr. Raval has also contributed significantly towards the development of gallium arsenide devices, and later he has also worked on technology transfer for production to the gallium arsenide foundry that is in Gatek, Hyderabad. Dr. Raval has many awards to his credit. He is a recipient of the Young Scientist of the Year Award, Technology Group Award, Best Paper Award, Outstanding Teamwork Award. That's very important. And DRDO Path-Breaking Research Award, Scientist of the Year Award, and Outstanding Reviewer Award by Elsevier. So as we see, he dons many caps. At present, Dr. Raval is the Technology Director and heading the development of gallium nitride HEMT devices for micropower applications. He is, of course, a very active author and has more than 100 research papers. And he's also guided several PhD students. We are fortunate that he has co-supervised some students with DU faculty, and his other students also from IIT. He's also been a reviewer for many prestigious international journals. With this, we are really very fortunate to have Dr. Raval with us, because he is going to give us an overview of what is happening at the national level and how academic institutions can partner and in this growth story, in our nation's growth story in semiconductors. With this, I invite Dr. Raval.
So good morning. I am really privileged to be part of this historic day. On this day, as Prime Minister has already launched 3 fabs, which are very, very critical for developed India. So as you all know that semiconductor chips are now part and parcel of our everyday life, and we cannot think of without semiconductors even a second or a minute. So, the government has already launched so many missions like quantum mission or artificial intelligence initiatives, or be it defense sector. Without semiconductor technology, we cannot become self-reliant in all these areas. So semiconductor is basically the backbone of all these missions. And being a part of the defense department, I mainly work for the defense applications. So whatever semiconductor technology I am working on is mainly for defense applications, but they are also used for several civilian applications. So, but our charter is to go for the defense, but there are many other initiatives which are coming up with these wide bandgap semiconductors for civilian applications. So, I am thankful to Professor Sanjeev, Professor Shyama, Professor Murdula ji for having me here on this day. Thank you very much. And I'm very happy to interact with all the young people on whose shoulders the main responsibility lies to take forward India in this important area of technology. So the topic what I have chosen is wide bandgap semiconductors, device technology for strategic RF applications. As I told you that I belong to defense, so our main area always focuses on the defense applications. And India is doing fairly well in terms of wide bandgap semiconductor technology. As Prime Minister already mentioned that we have thought of semiconductor fab or semiconductor initiatives right in 1962, but still no fab has come in India, and initially it was all silicon technology. But looking at the different properties of these semiconductors, there are certain categories which are very, very critical for defense applications. So we mainly work on wide bandgap semiconductors, and my complete talk is devoted to wide bandgap semiconductor, that too gallium nitride. So why we are going for gallium nitride? Gradually I'll build up the talk and try to make you understand what are the critical things which are very, very important and available in gallium nitride. So next slide. So I have organized my talk like this. I will start with the significance of gallium nitride semiconductor or variety of semiconductor, then why gallium nitride, then what is the market forecast, then what is GaN-HAM technology, then different device development approach, and then what is the status of technology in India, and then summarize the talk. So if you look at the silicon technology, the mainly advancement have taken place because of the process innovations. So as of today, we talk about the technology node. We are talking of 3 nanometer, 5 nanometer. So all these advancement in silicon technology have come up because of process innovations. But when we go to wide bandgap semiconductors, all the advancement have come up because of the material innovation. So material is very, very important here, because we are exploiting the properties of material to develop new generation of devices for our defense applications. And the main device which is used here is transistor, high electron mobility transistor. And as you, for the benefit of students, there is one term called heterostructure, and we dope wide bandgap semiconductor, and because electrons are always stable in lower energy level, so all electrons get transferred in a quantum well to lower bandgap material, where there is no impurity scattering and no Coulombic interaction. So electron move there with a very high mobility. So that is why the transistors which are based on heterostructures are called high electron mobility transistor. And this high electron mobility transistor is a 3-terminal device, and the positive bias at drain source leads to the current between source and drain, and negative or reverse bias at the gate controls the flow of that electron or current. So a small change in gate bias can induce very large change in the source drain current. So that is how we are able to get amplification out of these devices. So this is the principle mainly used for the power generation or amplification in these devices for critical for defense applications. And the most important parameter for high frequency is gate length. So smaller is the gate length, higher is the frequency of operation. And to have very high power out of these devices, you need to have very high current handling capability. That comes with the gate width. So you have to have a very small gate length and very high gate width to have high frequency and high power of application. Next slide. So if you look at the available wide bandgap semiconductors, you can see that indium phosphide, silicon carbide, gallium nitride, gallium arsenide. Gallium nitride wins over in various parameters. For high frequency, you have to have a very high electron mobility and very high saturation velocity. So these two terms are very high in gallium nitride. And gallium nitride only gives us the stable heterostructure with aluminum gallium nitride. So the new generation of devices based on HAMT for high frequency applications are mainly based on gallium nitride. Next slide, please. Next. So as I told you that gallium nitride is only second to silicon in terms of applications and various devices or systems coming up. And this spider clearly shows, which I just mentioned, that it gives you wide band gap, which is critical for high temperature of operation and also to have a very high critical electric field strength. And again, mobility. So all these parameters give you advantages in high frequency and high power applications. And if you look at lower this graph, it tells you that below 3 gigahertz, there are many competing technologies. But as you go above 3 gigahertz, there are very limited technologies are available, and gallium nitride wins over all these technologies because it provides very high energy power over the wide frequency range. So conventionally, all the systems, high frequency systems, are using gallium arsenide, but now gallium arsenide devices or systems are being replaced by gallium nitride because of the better electronic properties, high power density, almost 5 times high power density we are getting out of these devices. So your size and weight requirement reduces, which are very critical for airborne applications. So we are using these devices for ISA radars, as airborne radars, phased array radars, all the your fighter aircraft Tejas uses Uttam radar, which uses these trans-receive module based on gallium nitride because of only this advantage. Otherwise, their size and weight becomes very huge if you want to extract very high power. And then electronic warfare systems, because jamming application, you have to hop the frequency over a wide band gap range from say 5 gigahertz to 18 gigahertz. So these electronic warfare systems uses gallium nitride based devices. Then 5G, 6G communication. 5G communication all of you are using in your mobile phones. So this 5G communication is possible because of gallium nitride devices. Then 6G is coming up in a big way. Terahertz applications are coming up beyond 100 gigahertz we are talking. All this has been possible because of the advent of these devices. Then power electronics. As on today we are having electrical vehicle requirements. All power switching is based on these devices, be it silicon carbide or gallium nitride. Then satellite communication, data link, this software defined radio, all these have very critical defense applications. And this is this picture shows one of the ISA radar which is fitted in our fighter aircraft. So this contains almost 1000 to 1500 trans-receive modules, and each module contains 7 circuits or 7 MMICs. And if you look at gallium nitride R&D initiatives in India, in ham technology, various institutes are working. In fact, we are working with Delhi University in several projects, and we have had very good outcome in terms of simulation and Techade design of these devices. And ISC Bangalore, IIT Kanpur, IIT Delhi, IIT Bombay, almost with all the institutes we are working. And but one important thing is that all these institutes are working on discrete devices. But if you want to apply this technology in various systems, they need circuits, which are called microwave monolithic integrated circuits. So those circuits require passive components as well as active component, and then combination of these in the form of ICs. So that is only one or two institutes are working. Presently, as of now, SSPL, DRDO and IIT Mumbai is working, and one this GC initiative, GICI, this gallium nitride ecosystem enabler and incubator is coming up at ISC Bangalore, and they are setting up a foundry for gallium nitride devices. But at present, we have only one foundry available, that is with DRDO, established in Hyderabad. So we are the R&D backbone for that foundry. So I will briefly discuss what we are doing in that. And if you look at the international status, in 2019-20, the technology, the commercial technology is based on 150 nanometer gallium nitride, that is catering up to KU band applications, and only 4 foundries are there. And at SSPL, we have already developed this technology, and up to X band, we have already launched MMIC technology, and devices have been developed up to KU band. So I will briefly discuss the developments which have been done. And if you look at the publication coming up from India in wide bandgap semiconductor, they are fairly good, and lot of students are working in various groups, and currently India is ranking 5th in terms of publication. So in compound semiconductor, we have fairly good manpower, human resource. So it's right time, or it's high time to go for our own indigenous fabs, which Government of India has rightly understood the requirement and launched these important initiatives. So these foundries must be based on silicon technology as well as compound semiconductor technology based on the various requirement in different systems. Next. So if you look at the global market, the MMIC, GaN MMIC microwave monolithic integrated circuits, the compound annual growth rate is around 12%. And the present semiconductor market growth rate is around 5 to 6%. So you can see this, it is almost double because of the importance of these gallium nitride in defense systems, wireless infrastructure, which is 6G, 5G, and growing demand in your all mobile smartphone front end chip is based on these compound semiconductors. And the semiconductors which are available for this front end chip are gallium nitride, gallium arsenide, indium phosphide, silicon germanium. But for the meeting the requirement of SWAP, SWAP is one term which is used for size, weight, power. So all these size should be small, weight should be very small, and power should be high. So all these properties we are getting from gallium nitride. So that is why gallium nitride is coming up in a big way in all these sectors, be it a commercial sector or be it a defense sector. Next. And these are the foundries, and as I told you that you can see that in 2024, lot of initiative, gray color is aerospace, space and defense. Realizing the importance of these semiconductor materials, lot of development is going on in defense sector, and we are also developing these devices for our radar or missile seeker applications. And you can see in 2029, the wireless infrastructure is going to take over. That is, all 6G, 5G communication will be set up. So all those requirements are coming up. So this semiconductor technology is going to come up in a big way in next 5 to 6 years, and we cannot do away without having these indigenous devices in our own country. Next. And you can look at the business projections right now from 2022. from 1.3 billion to in next 5 years, it is going to be almost $3 billion business, and the main contributors are defense, aerospace, and wireless infrastructure. And you can see that GaN on silicon carbide, that I will these critical things I will discuss in due course. Next. So, realizing the importance of this semiconductor, initially SSPL was working on gallium arsenide technology. We started that project in 1993-94, set up our own foundry, and then once we developed that technology, realizing the importance, we started this gallium nitride technology initiative in 2008, and initially worked on epitaxy or material development, and as on today we have our own MMIC technology, we have indigenous circuits, and we are ready to launch our gallium nitride based MMICs for our radar and missile applications. Next. And this slide, very proudly we show that this is a press brief from Government of India, which certifies that the MMICs based on gallium arsenide are flying in our satellites, and that are based on our own indigenous technology. So this press brief tells you that in 2022, on 4th March, this satellite launched by ISRO uses almost 30,000 modules developed by our foundry using our indigenous technology. So this is all based on gallium arsenide, but considering the requirement, now we have shifted to gallium nitride technology. Next. And this gallium nitride, one disadvantage is that we don't have any native substrate. So we have to grow this material on a foreign substrate, and mainly 3 substrates are used, that is silicon carbide, silicon, and sapphire. But the silicon carbide is the best substrate because the lattice matching is lattice matching is perfect, in that only mismatch is 3%. But silicon carbide is a very, very expensive material. So, but it gives you the best performance. So, our all defense applications are performance driven, where performance is the most prime thing. So, for all defense application, the substrate used for gallium nitride technology is silicon carbide, whereas in electrical vehicle market or commercial applications for power switching, silicon substrate is being explored for development of these devices because it gives you cost effective solution. Next. So, at our place, we have followed the approach of gallium nitride. HAMT is the basic heart of these devices. So, it needs special heterostructure, then gate engineering, as initially I told you that gate length is the most important parameter. So, you need to print smaller and smaller gates, and then your source and drain contacts, these should be ohmic in nature, they should offer minimum of the resistance. And then special interconnection techniques, as you go higher up in the frequency in RF, the parasitic components or parasitics increase. So, you need to have technologies which can reduce these parasitics. So, all these technologies have been developed, and today we have, next slide. This is the material technology, this is the heterostructure which is developed or grown by metallo-organic chemical vapor deposition system. There are special techniques in which atom by atom deposition takes place. So, that is how the crystalline nature of semiconductors are maintained, but these are very, very expensive techniques and specialized techniques, but essential for development of these devices. Next. So, this is the main process technology, involves so many steps, and in this MOCVD, as I told you, and one important technique is lithography. So, most of the students are aware that lithography is used for printing the smaller dimensions, but here I am talking of 150 nanometer, 250 nanometer. So, this cannot be printed using optical lithography. So, we have to use electron beam lithography. So, electron beam is used to print such smaller features, and special systems are utilized for this, that is called electron beam lithography system, and this is available in our lab, and many of the students from Delhi University are already visiting and working on those systems. So if you would like to have closer look at these kind of facilities, please do come and visit our place. And this is the typical process flow in which these are the various steps of device fabrication. It is more than 70 steps are involved, but I have mentioned only major steps. And complete cycle for one wafer fabrication takes around 12 to 16 weeks, which is at par with the world standard. Even the best of the foundries worldwide are giving you time for complete fabrication of one wafer of 3 months. Next. And these are the critical things which I have already mentioned. I think we can skip. How much time do I have? 10 minutes. Okay. So, as I told you that the most critical parameter for having high frequency of operation is gate length. But gate length may not suffice because there are other parameters also which are critical. So, shape of the gate is equally important. Then the associated external capacitances are important. So, the major delay comes from the extrinsic capacitances which can be controlled by your gate engineering. So, all in fact your material structure or the thickness of your channel layer, that decides the capacitance. So, all these parameters are required to be optimized to achieve high frequency of operation. Only reducing gate length may not suffice. So, you have to have very good ohmic contact technology to have the minimum of source resistance and drain resistances. So, all these become very, very important for the technology to develop these devices. So, these all things have been developed at our place, and presently we are printing 150 nanometer of devices, giving us cutoff frequency of the order of 40 gigahertz. So, in these devices the convention is that if you want to use them for some frequency, your cutoff frequency should be at least 3 to 4 times of frequency of operation. So, that is how we decide the gate length parameter. If I want to use my devices up to X band, my gate length should be 250 nanometer, means the cutoff frequency I get is of the order of 35 gigahertz. And if I reduce my gate length to 150 nanometer, I get cutoff frequency of the order of 40 gigahertz. Next, 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 next. One other thing, as we are fabricating several devices over a wafer, so we need to electrically isolate all these components from each other. So, we need to break the conduction path between them. So, that can be done by two ways. Either you can etch the conducting area, or you can bombard with the nitrogen ions and damage that area so that there is no conductivity. So, for that ion implantation is done, and this system is available at our place, and this is very, very useful in developing planar devices. So, planar devices are normally give better performance than non-planar devices. So, presently we are using nitrogen implant for isolation of these devices, so that all devices are electrically isolated from each other, and wherever we want to conduct, we form the transmission lines or conducting paths using metal lines. Next. And this I want to just show to the students that the first one is the scanning electron micrograph of 250 nanometer. So, any idea what is 250 nanometer? What is the thickness of your hair? Anybody? How much is thickness of the paper which you use daily for the writing? What is the thickness of that paper? It is 100 microns, 60 microns. So, I am talking about 0.25 microns. So, you can realize the dimensions I am talking. And these are the dimensions which we are doing by electron beam lithography, because they are normally this printing is limited by the wavelength which you are using. So, we have to go to such a smaller wavelengths. Next, 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 or next. So, these are the different devices which we have fabricated. So for different applications, you can see the number of finger interdigitated structure. So we want to have high current handling capability for power application. So my device size will be bigger. For low noise application, I want to have very, very small noise and smaller gate resistances and parasitic capacitances. So my device size will be less. So the beauty of this gallium nitride technology is that all three, either it is switch or amplifier or low noise amplifier, you can have them on the same chip. So complete TR module or front end chip can be fabricated on a single chip. So that gives you advantage in terms of performance as well as size and weight. So these kind of circuits are called trans-receive chips or system on chips. So that is possible because of the material available for all three kind of circuits in the same wafer. Next, next, next. And for going to the KU band, as I told you, we have to reduce my gate length to 150 nanometer. So this is the real 150 or 140 nanometer dimension printed by electron beam lithography, and then dry etching or plasma etching is being done to remove the material selectively, and then gate metal or nickel gold metal is placed and devices are fabricated. Next. So these are the devices which are working up to KU band with the 0.15 micron or 150 nanometer, and this is air bridge. You can see that the metal line is lifted. So these metal crossovers offer capacitances over these devices. So to have minimum of this overlay capacitance, we need to have a dielectric underneath which has got minimum dielectric constant. So minimum dielectric constant is of air. So we lift this metal lines. There are techniques in which we can fabricate. So all these source fingers or drain fingers are connected to have high current handling capability with these interconnections which are called air bridge interconnection. And similarly, in all these circuits we use common source configuration. Source is required to be grounded, and for grounding either you can use wire bonds, but they offer inductance at high frequency. So normally in these circuits what is done, backside is your ground plane and a hole is etched from backside using dry etching, and the connection is made to the source to achieve the source grounding, and this offers minimum of inductance and gives you advantages in gain of the device at high frequencies. So all these technologies are essential if you want to develop the devices for working up to KU band or beyond. So all these have been developed and available at our place. Next. And if you look at, we are presently working at 4 nodes. The gate length is 0.7 micron, 0.4 micron, 0.25 micron and 0.15 micron. So depending on your frequency requirement, you can choose the technology node. The first 0.7 node is normally printed by optical lithography, in which we are using UV light of 365 nanometers. Otherwise, all 3 nodes other are done by electron beam lithography. And you see that this is the curve which is giving you the cutoff frequency at 0.15 or 0.17 of 44 gigahertz. Next. And these are the power devices in which one single device is giving power of the order of 130 watt in L band. So you can see that the power handling capability can be increased by increasing the number of fingers, interdigitated structures, because this interdigitated structure gives me high gate width with reduced parasitic resistances. So this kind of structures are used, and these devices are required for radar applications. So we have developed these, but one single device contains more than 60-70 gate fingers, and all these gate fingers are required to be functional. Even if one small defect in a gate finger may kill the complete device. So yield is very, very critical in these devices, and these all have been developed and tested at our place, and we are now transferring this technology to Gatek Hyderabad for production. Next. Next. And as I told you, for these single devices are rarely used in systems, so we need to have circuits. So for circuits you need to have passive components also. So these are the passive components in which inductor, capacitor, transmission line, nickel chrome resistor, all these components have been developed, and then these components are developed and then converted into process design kit or in models, because designer cannot use these devices just like that. He has to have a electronic models for using them. That is called PDK. So process design kit is specific to a foundry capability. Each foundry has to have its own process design kit for the customers who can use that foundry for developing circuits. So now we have our own PDK. Next. These are the wafers, that is active component wafer, in which thousands of HAMs are fabricated. This is passive component wafer. These are extensively measured and models have been extracted and PDK is released. So PDK is available in from any foundry to use that foundry for development of your customized circuits. Next. So we have our own PDK. It is launched now and available for different users. Although presently we are catering for requirement of only space and defense requirements. But very soon we are going to launch it for our commercial applications also. Next. So once we have developed our active and passive components using our PDK, we have designed these different circuits in gallium nitride technology, which is very few countries are having, and these MMICs are highly guarded because of their critical defense applications. They are not very easily available. If you buy in small numbers, they will give you, but once you go for large number for development of systems, they can be denied because of their strategic applications. So we have now developed complete technology at our place, and these are the first set of circuits which have been designed, fabricated and tested. So this is how one tile looks like, in which different circuits of low noise amplifier, power amplifier and switch are available. Next. And this is the wafer which is fabricated, all these now MMICs have been tested. Next. These are the fabricated MMICs tested. First one is power amplifier, and these are catering up to X band. And these have been tested, and very soon we are going to roll out our first product from foundry. These are initially they are developed as a part of a project to establish the technology, and now we will be developing these MMICs as per the requirement of our customers, which are mainly our sister labs and space department. Next. And one important thing is that in the process of technology development, characterization is very critical. So normally RF characterization requires packaging of device, bonding and then doing the measurement, but that is a very time consuming process. So here we have developed on wafer measurement capability. Directly the probing can be done on wafer level even in the circuits. So these gives you very quick feedback, and this has been enabled by using probe cards. So especially designed probe cards are available. We have designed our own customized probe cards, and we are directly measuring wafer level these circuits to have a quick feedback. Next. These are other circuits which we have developed, and this has given us a lot of confidence that the first set of MMICs based on our PDK and external PDK we have designed and fabricated have given the desired performance. Next. So to sum up the talk, we have developed first HAM technology based on 4 nodes. One is 0.7 micron, 0.4 micron, 0.25 micron, 0.15 micron, and then develop passive components, then develop the PDK, process design kit. Process design kit is basically the replica of the foundry capability. The process which a foundry is having is basically given to the users in the form of PDK, which they can use. And then we have demonstrated different circuits, MMICs, showing the capability of our technology, and at the same time to establish a design capability, we have gone for wide bandgap MMICs also, catering from C to KU band. That is very wide bandgap capability, and very few countries are at present, as on today, are having this kind of technology. So with this, I would like to thank with the acknowledgement to my team. This is my team at SSPL. Of course, acknowledgement to Delhi University for working with us. Thank you very much.
Thank you so much.
I'll be happy to answer if there is any question.
Yeah, I think now we are all very excited, and I think this is a perfect timing. And I'm joined by other colleague from SSPL, Mr.
Okay.
Dr. Datta. May I invite you to please come on the dais, and so that, and Professor Shyama. And I think I would like to take the maximum advantage of this gathering to have a little interactive discussion among the students and the experts what we have received. And another colleague, Dr. Sanjay Tomar, can also join us for stage. It's fine if you're there. Right. Thank you. So Dr. Datta is where is has he gone? Dr. Datta, I think we would like to have your opinions on certain questions and all. Please be here. So I think the domains of HAMS and all already have been covered. So may I invite any of the observation on the semiconductor policy of India from the students? So I would request our experts today to answer those queries. Anyone? Yes.
Is it okay?
Yeah.
Thank you. So my question is related to the applications of the HEMT we have developed. And as you have said, we are working on 150 nanometer, which caters to roughly 40 gigahertz of 40 gigahertz frequencies. But as you mentioned in your talk that we are estimating up to 3 to 4 times than what we'll be using it for. So that calculates to around 10 gigahertz, which is like usable frequencies. 10 to 15 gigahertz. So I would like to know that what kind of applications are we targeting in 10 to 15 gigahertz? Because 5G and 6G is like roughly ranges from 6 to 10 gigahertz at max.
5G can be taken care of because in 5G there are 3 frequency ranges. So one is sub 6.
Can you just please use the mic?
One is sub 6. So sub 6 India is presently working on sub 6, and then 27 gigahertz and 37 gigahertz. These are the 3 frequencies. But presently we are catering for sub 6, and if in 5G application, if you require lower gain, because I told you that this 3 to 4 times requirement comes for power application,
yes,
where you need substantial gain and power. But if you can manage with low power and low gain, as in communication applications, we can go up to 30 gigahertz with our 150 nanometer.
Okay, thank you.
Great. Any other observation or question? Because, you know, this is the right forum, and it's the right time, because, you know, it's not necessarily that the students belonging to the electronics domain are the part of the semiconductor policies. Even the economic students, social sciences students, humanities, they have to take the active part to make these semiconductor policies a successful story. Why? Because everyone is required to contribute in a different ways, because as you have heard from our expert, and they would give more light onto that, each one of us has to contribute in different dimensions, right from design, architecture, even the integration of those complex circuits and all. And the most important thing which is coming up, which is the IP core. And IP core is something where all of us, we can contribute and make it happen so that the portability can be achieved in the design and in fact the manufacturing of the semiconductor devices. Dr. Datta, would you like to add something to it on IP core and all? No problem, but you can be extempore.
Actually, what you are saying, that it is, of course, it is not only a engineering or science issue, because to get a success in terms of in totality, we have to think of changing the dimensions in the term of, you know, the Techade. That means the decade enabled by technologies. So that is the thing. So that decade enabled by technology is not only related to the industry of semiconductor only, but this semiconductor driven, because as our Honorable Prime Minister has said that about Industry 4.0, that means that it is a industry that will be revolutionized by the use of this indigenous development of semiconductor chips and semiconductor based sensors for our future generation for betterment of our overall life. So that's
Great, thank you. So, how many students from chemistry do we have here? Chemistry students? Physics? Students from physics? You don't call your own students.
So maybe I would also,
Yeah.
we have people from the commerce department also. And you know, one of the challenges during, in the last 2-3 years was we were not getting equipment. There were delayed, people who were trying to get phones and computers, there was delays. Right, so this is now again highlighting why we need indigenous industries. And also there was recently Rajya Sabha question also where we are importing 90% of chips. So we need to somehow change that. From import, we have to now, in the next 10 years, like I told you earlier, this is a huge market, $1 trillion market, and what should be our goalpost? This is for the commerce, this thing, and 5%, 10% in the next decade, the Techade that we are talking about. So what can we achieve? That is one thing. Now for the students, we had you will very soon reach where Dr. Raval has reached. I will just show you what a wafer looks like. I will not allow Professor Sanjeev Singh to touch it because he is not wearing gloves. And these require high-end facilities. We are very fortunate that we have SSPL in our neighborhood. Let us take up their offer, go and visit and see how devices are made. Before making the devices within our university, we have lot of facilities where we have person here who's Professor Binay Kumar, who's a specialist in crystal growth. We have a science instrumentation centers where Professor Raval talked about assessment of material. That can be done within our university. Then when we go to the device stage, we hop over to SSPL, use the lithography facilities, make devices. So we have to look at partnership if we want to involve ourselves in the semiconductor mission. Academic institutions, it's very important.
Yes.
दिख रहा है? This is a silicon wafer. Silicon तो पढ़ा है आपने? हाँ, आके मुझे बाद में पूछ लीजिएगा ये P टाइप है या N टाइप है? दिखने से पता चलेगा?
नहीं.
नहीं पता चलेगा ना? But anyway, that is the starting point. देखो एक सेमीकंडक्टर से दूसरे सेमीकंडक्टर तक दिख रहा है? चलिए, I think
Anyway, but this is a very small piece of, demonstration, but what this wafer is being utilized by our great scientists here, and they are fabricating different kind of devices which are being used even in the missile technologies. Even the day before yesterday, Agni 5 was launched, so there is a very strong component of electronics is playing there for the guided missiles and all those kind of things. Not only the semiconductor, the communication, and all sort of, technological, ecosystem is building around. So that is why the self-reliance concept is coming up, and that is why all of us, we are sitting together to envisage the new dimensions and how we can contribute to it and how we can. And on the top of it, I would like to add one more thing that our very dear registrar, Dr. Vikas Gupta, has joined us. And why he couldn't resist himself, because he is an avid electronic scientist and he has worked a lot in this domain, but now he is administering the university. But it is a very good sign that he is taking care of the technological aspects of the institutional requirement, and he is so keen in making this university a very, very enabled in terms of the technology. So I would like to invite Dr. Vikas Gupta to just address few words and his experience also.
Thank you so much, Sanjeev ji. More than 30 years ago, I was into electronics, but I left now. But I think today's initiative of the Honorable Prime Minister will be a big game changer. With small initiatives he has taken, we have been dependent upon the ICs and other circuitries which we used to get from outside. I remember my old days that for fabricating a project, we used to visit various places for looking for ICs and other circuits, and we were not able to get that. Professor Shamarat was showing the fabrication just now. I remember one of the ICs we programmed, it was programmed inadvertently, and then we wanted to erase it. We were not having that laser facility to erase the program which was there in the IC chip. And we went to SSPL to get that laser light on it so that the erasure is there, and then we have to reprogram it. And it was very difficult to get those ICs. Now I think with this is going to be a big game changer now. That the circuitry which we are importing, which we are dependent on outside, would be manufactured here. Sanjeev has already told that the kind of initiatives our DRDO labs has taken, the CSR labs have taken, we are slowly moving in that direction that by 2047 we definitely will be a Viksit Bharat, as has been the vision of our Honorable Prime Minister. So through this young generation, through these bright minds which are here with us, we hope that we should be able to achieve the dream of Viksit Bharat much before 2047. My best wishes to all of you, and thank you so much to all the experts who have joined here today for this program, and thanks to Sanjeev Singh for organizing this event in such a big fashion. Thank you so much.
Thank you so very much. May I invite our dignitaries to please join us on the floor. So I think upar. So yes. So I request Dr. Gupta to felicitate our guests and experts who have come from DRDO to deliver the keynote address. एक मिनट
all of us to be at a platform so that everybody is aware of the chip.
Yes. May I invite Dr. Sanjay Tomar? Dr. Tomar, please. Thank you so much.
I can share one more experience with you. Way back in 1995, that All India Council for Technical Education, the then chairman, Professor S.K. Khanna, we all know that the technical education was very much advanced in the southern part of the India. He advised one of the colleges, flourishing colleges, to start a course in robotics or artificial intelligence. But the mindset was that the Vice Chancellor of the affiliating university was not ready to start the course. And now you see this, the robotics on these things, which are a buzzword now, we see in every application. So our mindset is like that, that we don't want to venture into the new initiatives. A fear factor is always there. But now, with the efforts of our Honorable Prime Minister, with his vision, with his commitment, with his dedication, with his sincerity, at least he is pushing all of us to be on a platform where we see the technological advancement everywhere. So we see we should we should try to achieve our motives, we should try to achieve our vision without fearing for the result, and then we will be soon coming out with the flying colors. Thank you so much once again.
So finally, I would like to call upon our joint registrar, Mr. Joy Chand, to just make a special announcement for the students and the people who has worked very hard since yesterday to make these things happen. So you can use the podium as well.
Yeah, actually a wonderful program on semiconductor projects, and we can see the dignitaries here and the scientists who have made you understand. And before that, we had a wonderful session where it was inaugurated by our Honorable Prime Minister. And in this entire initiative in this University of Delhi, a lot of efforts have gone into it, and I'd like to particularly thank Professor Sanjeev Singh, Professor Shyama Rath, Dr. Vikas Gupta, our registrar, and the back-end team, who have worked very hard into this, and under the mentorship of our Honorable Vice Chancellor, Dean of Colleges, Director South Campus, and we have tried to put things together. And I think that everything has gone exactly the way we wanted it to be. And thanks to all of you for overwhelmingly joining this program, and best wishes to all of you for your future in academics and in professional life and your personal endeavors. Just this program is now getting concluded. Please join us for refreshment on your left side while you make an exit. Thank you.
Thank you so much. We'll have more such interactions in the near future. Thank you so much.